Okay, so good evening, everyone who are from India and the parts of the world where it is evening, and good morning and good afternoon from wherever you are. I am R. Hariharan, the head of academic affairs at Raising a Mathematician Foundation, and it gives me immense pleasure to welcome you all for this fantastic conversation that we have planned, uh, titled "Can You Physics a Math?" As you all must be wondering, what does the title mean? I hope the conversation between the two speakers, by the end of the conversation, you would have figured out why this title was given for this talk. So, Can You Physics a Math is a conversation between two physicists. We have Hariom Jani with us, who is the faculty at National University of Singapore. He is doing his postdoctoral fellowship at NUS, and he completed his PhD from National University of Singapore, and he has been awarded the prestigious Arthur Novick Student Award for Teaching and Silver Graduate Student Award for Research for his extensive teaching and research initiatives by Material Research Society, Boston. So he does research in physics and material sciences at NUS. And we have a theoretical physicist with us. His name is Shyam Shyam Wuppuluri, and he has written many books on foundations of science, and he is the recipient of the prestigious Einstein Fellow for the year 2020 for his project on From Electrons to Elephants and Elections, Grand Unified Narrative on Content and Context. And Shyam is the first fellow to be elected under natural sciences and the first Indian to receive this prestigious fellowship. So it gives me immense pleasure to welcome both our speakers. So for today's conversation, we don't have a specific format because we thought that it will be nice to have this conversation in a fluid manner and let the conversation take its own course. And we focus so much on instructed or the structured form of learning that we forget that a lot of learning that happens in our life is through unstructured means. For example, how do we learn to operate a cell phone? There is no coaching institute that teaches us how to operate the cell phones. It's through unstructured learning we figure out, we explore, and we learn. So there are a lot of things in life that we learn from discussions, from conversation, by hearing people who have the necessary experience. So today, the way we are thinking about this talk, when we spoke with Hariom and Shyam, is that we always think about physics, but we cannot think about physics in isolation to mathematics. So what has been the role of mathematics in sciences historically? And how is the thought process different in math versus science? And since Hariom is an experimental physicist and Shyam is a theoretical physicist, how is the approach between this experimental and theoretical aspect of sciences different, and how do they converge? So it seems that they are at loggerheads, but at the same time, they seem to come up with a nice unified story about sciences. And since they are also researchers, and research can get sometimes frustrating, it would be nice if they can also share what is the reality of practicing science on a daily basis professionally. And also we would like to know where the current status of the subject, what is the current status of the subject and where it is headed. And then we will take up whatever comes up and whatever questions that are asked, and based on that we will follow the conversation in that direction. So let me ask Hariom to start the conversation. Over to you, Hariom.
Thank you for the generous introduction. I just want to clarify that I'm not a faculty, I'm just a researcher. Faculty is a very specific term, but the very much a researcher of physics, right? So thank you so much for inviting me here. And I'm so pleased to have this dialogue with Shyam in front of all these budding researchers and in front of all these students who are so passionate about mathematics, about science, and particularly about academics in general. And a little bit how I would like to start off this conversation. And I think given that this is Raising a Mathematician, it is important to recognize the significance and importance that mathematics has played in shaping science as it stands today. It started off in various cultures, in Chinese, in Indian culture, in Greek, various Middle Eastern cultures, where pursuit of knowledge began, and everywhere they had a certain approach to investigating the world around them. And a very simple way to think about it is that if you imagine you were 2,000 years ago, you were a farmer, right? And you just go out on the field, you have toil throughout the day, and in the evening you have this very beautiful sunset, and after that you see a star-littered sky, and then you start to sit down and wonder, how these stars are there, and you notice, oh, there is a certain pattern in the stars, and it tends to repeat itself. And when patterns tend to repeat itself, that is how there is a genesis or a manifestation of thinking process that, okay, these patterns tend to repeat themselves. Maybe there is some reason why they happen that particular way. And the whole field of what was then called natural philosophy emerged from there, which we today more or less call science. It's very interesting because the roots of science very much lie in philosophy or logic, and we have discovered that till today. But that phase of science as purely natural philosophy almost continued for about 1,500 years, or even more, about 2,000 years, until very recently, until the time of Renaissance, when things changed very dramatically, and the rate at which science started growing became exponential. And I think the root cause of that, at least to me, I feel, is that mathematics was brought in as a tool and language to discuss scientific phenomena. And that really accelerated the whole field, because, this very beautiful quote that one of the very famous Nobel Prize winning physicists has said, Richard Feynman, he says that mathematics is almost like the language of nature. And once we figured out how nature talks, then, we can understand what nature is trying to tell us, right? So I think that they're really beautifully married to each other. And there is a very deep understanding that perhaps has evaded many people why it is so effective, that why is mathematics so effective in describing nature. But probably I think Shyam will have very valuable comments to add at this point. So I think at least that the mathematics is really crucial for science, and to take it and shape it for us to understand and shape the world.
Okay. So I think that's about that. I think Hariom has summarized most of the things that to set a beautiful context. But what I would try to do is that, I so far as more than any particular thing like a physicist or a mathematician, I always have been primarily an admirer of ideas. I would best call myself that, because I don't have a specific interest or expertise in a field for a long time. What I am is an admirer of ideas, and I think whatever brings me closer to the truth is what I would pursue. And I think that is how me being a human, and I think applying the standard laws of logic that, if all humans have this general tendency, I think that's how the science has started about. And if you read Philosophia Naturalis Principia Mathematica of Newton, Newton called it the natural philosophy, principle of mathematics and natural philosophy. So there was no word called science those days, because I think it's philosophy that has connected. It's a sort of a container that has held within it all bunch of questions within it, that starts from how should one live their life, what is ethical to do, what is it to be good, what are good actions, And in the same way, you always have to think that we are embedded inside the world. I mean, Heidegger very famously says that we are thrown into this world. So the way we are thrown into this world, we are always embedded around the world. So these questions slowly seeped into the nature of the world and nature of the surroundings, and how much we can influence the world, and how much world influences us, and thereby influences our influence of the world. It's a very complicated thing. So not only we structure the world around us every second, even the world helps us structure our structure of the world. So if you are familiar with the basic notion of functions, it's something like F circle G. I don't know if you have studied compositions. I think it's not only that a function is it's not only a function from you to the world, it's also from you world to you and you to the world. So this is an ongoing process that started from Newton and so on and so forth. But one of the very big advantages of Newton, Hume, Leibniz till Berkeley was that I like to summarize fields. I mean, I don't like to look at a subject as its own theorems and formalisms. I think that's very mechanistic way of looking about it, and I think that's very good approach that people have been doing so far. I think I'm not saying that I should totally discredit that, but I think if you have to summarize a field of physics together, what exactly is physics altogether? I think a simplest explanation that I can give is that physics is a box. Okay, physics is a box. Now this magical box always gives us something. I mean, it should not be trivial. You cannot just take a carton and then say, oh, this can be physics also. Physics is a box that gives us some meaningful information, and how it does it is very, very particular. So you input a certain set of laws into the box, you throw that set of laws into the box, and you throw the state of universe into the box. You put these two things into the box, and you stand outside the box. This is also quite important. You stand outside the box, and then after you close the box and mix it a while for a lot of time, and then open it, you get all this combinatorial explosion of results that are coming out of it. So this has been the notion of physics so far, and people cannot have any issue looking at physics this way, because people always thought that laws are given, and even the state of the universe is given. And they had very simple explanation for that. Who did that? God. Newton, Leibniz, till the time of Berkeley, they all believed that God solved it. And I think that has not, though there were very trivial sort of issues within the sciences, but I think the major roadblock has been removed, because you don't have to question. I mean, it's all in the place. All we have to do is that we have to extract these things and extract some meaningful information out of them. But the issue came, as Hariom rightly said, when the Renaissance took place, and people thought that, okay, maybe God is good, but let him handle bigger stuff, but let him not peep into our bedrooms and our lives and control us. So I think people have just removed this God. And the moment you remove this God, the question again arises that how is it that this state of the universe was in such a way that it was? And how is it that the laws of nature are the way they are? And I think it's very important that people always think that physics is all about predictions. I mean, of course, a fair amount of it is all about predictions, and that's what physics is about. But if physics is purely about predictions, I don't think any time that Einstein would have gone ahead and made relativity out of it, because practically you don't see things. I mean, at least Einstein did not see things traveling at the speed of light. It was only a thought experiment. So I think what was the issue is that it's not driving the observations. I mean, observations, of course, they converge, at least in a limit. What drives us is this nature of loss. And this nature of loss, by definition, have to evolve, because you cannot have one set of laws governing everything. And again, I'm trying to simplify as much as I can, and let me see if I can get a coherent whole out of this. So what I started out by saying was that the initial state of the universe and the laws that we put into this box are given by the God. Now you remove the God and out of the picture, now you have a very big paradox. And those days, because there are a lot of assumptions about God, I think these sort of cultural memes, and not meme in the sense of Facebook meme in a deeper sense, what Schrodinger and Richard Dawkins calls as memes. You should always believe that these are the things, as students of science, I always tell my students that you should be very, very comfortable knowing that science or physics on its own accord is not an isolated endeavor. Society, politics, your beliefs, your culture has a huge influence about it. And Newton, for instance, I mean, those days people had no issue believing at action at a distance. Suppose you have magnets and you ask how do magnets work, people thought, oh, there is an action at a distance, we don't know about it. But Newton was a very honest man. He knew the problems with the action at a distance, but he thought, okay, that can be explained away. But he realized that, okay, if you suppress that, everything can be combined together. So there is always this sort of strange inversion of logic that took place. If you take Newton, for instance, there are three people that I can definitely remember: Newton, Darwin, and Turing. These three people are my most favorite examples. So Newton thought that, why is it that apple always falls to the ground, not the moon? Why doesn't moon fall onto the ground? And he had this very strange inversion. So it's always about extending your own worldview. So it's not just that you ask and you are sufficient with only explaining that why is it that apple falls from the tree to the ground. You should also be able to explain that in the same way. I think Vinay has spoken about the induction yesterday. So I think you should also be able to induce that why is it that moon is not falling down in the same way. So he had this very strange inversion of logic where he figured out this inverse square law that connected the heavens and earth. That is a very big connection. The next beautiful quantum leap took place when Darwin has figured out that you don't need an intelligent designer in place. From the laws that are mechanistic, that are mindless, meaningless, and driven by sort of an automata, you can get Beethoven, Mozart, Shakespeare, and Zoom and our conversations, everything in place. So it's actually connecting on one side a very mechanistic world, and on the other side very beautiful world of art, science, and all that we find worth doing. So this is another sort of interesting connection that people have made. And the third thing is, of course, Turing. Turing thought that you don't need to have a very intelligent and beautiful mind to do mathematics. At least the basic foundations of mathematics. He reproduced that using very basic set of very mechanistic axioms, like how your calculators perform, for instance. Turing was, of course, the first proponent of a sort of a thing that we call now as computer. But he thought that how you can program this thing into meaningless things, and using these things, somehow the mathematics can pop out of it. So if you see these strange connections that are there in the history, what drove them was not always the predictions. Because if it's the predictions, world would have been perfectly all right. We would not have ever needed this thing to step out and figure that out. What drove them was this innate understanding of this laws and how do they fit together in the picture of the world. So unless, and one of the thing is that human is always greedy. So whenever you find some unsolved question or unsolved puzzle, people just try to somehow fix it temporarily, and all the rest of the thing in physics, when you learn how to write funding proposals, you know, a lot called fudge factors. You fudge a lot of things in, and then that's a way of sweeping under the carpet. I mean, not a lot of researchers do that, who are honest, but mostly we know that most of the theories are at most provisional. That's the best word to put it. They're provisional, and we pretty much know why they're provisional and why there is a scope for improvement. And I think this is what separates the science from the religion, that it is in a sense a very dynamic thing that, of course, destines its own proving itself as wrong. So it's a beautiful enterprise which itself says that, I have to be proven wrong for my own improvement. So it's that sort of a thing that scientific enterprise has always been about. And I think that gives a lot of freedom, because Richard Feynman again famously said, the only way to end physics is to do experiments given our own theoretical constructs and keep repeating them, so that you have dead science at the end of the day. You don't have anything new coming out of it. The only way that new science come about is when you have some sort of an experiment that fails, and that leads to a whole lot of quantum leap of things. So I think I'll stop here, and I think I'll come back again. Yeah.
So Shyam, there is one question that is coming up from the students. Shreyan wants to know, does that imply the theory of everything is how this box works?
Okay, so the theory of everything, if you want to speak about that, of course, we very well know that theory of everything is impossible. You cannot have a theory of everything. Let me give a very dumbed down version of theory of everything. You need, if you have to have a theory of everything, it's as similar as saying that, you know, you have, suppose you have a box, okay? You have a box, and let's take the box example of physics again. You have to put down everything that is physical. Okay, so everything, what is the stuff of the universe? Okay, what do you start putting in? So one thing that one does put in is that maybe my cell phone, I'll put in the box, my spectacles, my hair, my a washing machine. So you keep putting one by one every object into the box. What about objects like numbers that are not greater than 5? Would you put them inside the box? Of course you put them inside the box. Numbers that are not 5, numbers that are not 4, which is the negation of 4, and numbers, what about our thinking? Do we put our thinking into the box? Do we put electrons also into the box? Which is to say that if I put a cup into the box, would I write down? At the end of the day, assume that it's relevant to the present situation. We have to go to the grocery store, and we have to go and ask a physicist sitting under the grocery store that these are the things that we want. Do we write there, okay, electrons, quarks, protons, and also mountains, elephants, and computers? Is that redundant? So if we have a theory of everything, and to prove that it's a theory of everything in a very strict sense, a theory of everything has to support its own conclusion. A theory of everything has to prove itself. And by definition, that fails, because if it proves itself, it just becomes another version of an eccentric or an very egocentric person that says that, oh, I'm the proof of my own thing. And if you want to go into very technical thing, there are very good theorems of Gödel, Kurt Gödel, who is a logician, who proved that how theory of everything is never possible. Because if you have theory of everything, which means that it explains everything, and ipso it explains itself. So I can only compare it to a very famous person who was a Munchausen of Baroque. So what he tried to do is that he sat in, he threw himself into the pond, and he started pulling himself by pulling his own hair. So you that is a sort of a theory of everything. You cannot do that. When you know fulcrum and force and power, you know that this thing cannot work, but ideally it does work. If you do not see where this hand and body are connected, you always think that it does work. But when you zoom out, you see that you are yourself pulling yourself out of the mess. It cannot work. Yeah.
I think this question that Shyam has raised is very fascinating, because it goes to the heart of how do we think of the long-term picture of physics, right? So, of course, there are many unsolved questions in physics. There is a grander picture in physics. I don't want to address that at the moment just yet. But what is the spirit in which we do physics, or sciences in general, not just physics, right? Is something very interesting to think about, and it comes back to the point that Shyam made. Can you make a box which is entirely complete, a box which includes that box itself? You know, it's a very strange tautology, right? And it's never going to happen. The reason why I think science is interesting is that when I started off on this journey as a younger boy, very naive, to be very honest, I used to think, okay, science is going to be one approach where I use logic to gain the picture into the truth. And it was very philosophically charged kind of thinking process for me, because, like, you know what, I want to get truth. And, you know, the idealism of adolescence was always there, and which inspired me to think that way. And then as I progressed into the mechanistic workings of science, I realized that actually the business of science, while it might seem that you're going towards the truth, can we actually go towards the absolute truth? Can we at one point say, okay, this is the end point of investigation, right? Or as Feynman is called, the death of science. Can you actually have something like that, right? And what would that look like? So inherently, if you look at the scientific method works in a particular cyclical manner. That you say, I have a certain experimental observation. I then prepare a hypothesis to explain that experimental observation. I have an elaborate theory based on that hypothesis. Based on that theory, I make certain predictions, okay, which is only a part of the game, as Shyam has already clarified. And those predictions then either match with the experimental fact and conform with new experimental fact, or they don't. And at which point the loop completes, right? So then you have this entire cycle where you can confirm or reject the hypothesis, and therefore the cycle follows. Now, can this loop take us to absolute truth? And it's a very fascinating question. We might be tempted to think that it may, but I don't know if it ever there is an end point of this entire investigation, because the game is very simply not in our hands. The game is in the hands of nature, because you start off with the investigation, and you start off with the knowledge and bias. And I choose the word bias very carefully because we are biased by the knowledge that we have, right? Our vision of the entire universe is biased by the knowledge that we currently have. And we develop a theory based on that. And then we go, that bias takes us through logical, rational approach outside that bias, then makes us explore new realms, exactly as Einstein showed us relativity, right? I mean, he was 100 years ahead of his time in terms of thinking, or probably some might believe, no, he wasn't, but let's let that debate aside. But he pushed us into a new realm of thinking that people were not thinking at that time. We got there as we do today. We know gravitational waves are real. We have a LIGO detector which proves that. We can even know black holes are undergoing collision. We have seen a photo of a black hole just very recently. So we know that these things are actually there. And now that we are in this paradigm, we start making new kinds of predictions and theories, which then hurtles us further. And so it's like a ever expanding universe, right? What is the boundary of the universe? There is no boundary. I mean, it just keeps on expanding every time you push the knowledge. So I think it's very fascinating because we often tend to come into this pursuit very much with a perspective of getting to know the truth. While it is a beautiful and very noble pursuit, you need to know that it is not the correct way of thinking here, because the scientific method is a feedback loop, and every time we keep on defeating our older ideas and getting better and better and better over time. And in this sense, inherently, it is very different from various other pursuits. And I must make this remark particularly, one can say in the sense is very different from religion, okay, in which there is a clear endpoint, or for example, even mathematics. So mathematics is a very interesting body of knowledge where you develop a certain coherent logical structure. And as far as that structure is entirely apt in itself, it's a nice box. And in that box, there are a few other small boxes. They fit nicely and it works like that. Now, that box and another box may talk to each other or may not talk to each other at all. And the universe of math cannot be disproven. But that is very different from the pursuit of science, because you have a certain approach, you've developed a model, and then nature says, I don't think so. That's not enough yet. And then we go back to the drawing board, and then we're like, okay, let me revisit the thinking process here. And then we go back at it again. And we're like, okay, nature, I've got one more better idea. Does it work now? Nature says, okay, I'll allow it for the time being, you know, and then it keeps on going like that. So I think it's a very, very fascinating approach in science that I think we should be aware of and be mindful of, that we go towards better and broader knowledge with time.
So Shyam, there is one question that has come up. Maybe Shyam or Hariom, both of you can answer this. So in the 20th century, we have seen big discoveries or big inventions or big ideas that came in physics. Are there big ideas that are still coming up, or has it, has the big ideas reduced in the near future? In the near past? And what do you think about the way the physics is moving? Do you want to take it now, or you can take it later? If you think that this is not the right time, we can take it later.
I think it's a fair question. I mean, before that, I just thought about another thing to just append to what Hariom said, which is fantastic. I think the induction that he just spoke about has a very important role to play between the mathematics and physics in that sense. So I saw a very interesting thing, and I could not stay through the whole talk. And Vinay had a slide that spoke about a dominoes problem of induction, that you have an infinite set of dominoes, and if the one domino falls, the domino at the end has to fall. So that's the sort of an induction that he tried to prove, the principles of mathematical induction. I don't know if he proved it or if he disproved it. I did not stay till the end of the thing. So I think that gives mathematicians this extreme luxury of imagining these sort of toy models, because they, in a sense, have pride in a very truest sense, because they are not answerable to anybody. Nobody is going to ask, catch their collar and ask that, why, how do you speak so? But when you actually transfer it back to physics, there are a lot of problems that may come. maybe during this infinite tipping of dominoes, maybe it does of course take infinite time if you induce that again mathematically. Maybe universe by then would stop expanding, and then there is a big crunch that starts happening because gravitational constant becomes negative, then it starts attracting, then maybe the dominoes won't fall. So when you just expand a bit of math and leak it into physics, that's when you see that it's an enormous set of demons that you have to address. If it's purely max, so I think that relates to the present question also at the hand, that in olden days I think people had very less innovations or breakthroughs that so to speak. I think that connects to two aspects. One is the thing called complexity, and another thing is something called interrelatedness, which is to say that in olden days one person had knowledge of most of the fields, and that is of course, I'm not demeaning them, that it of course takes a lot of intellect those days to grasp all these fields, but it was doable. There were, for instance, if you take Fermat, he was a lawyer. If you take Newton, he had knowledge of physics, maths, and multiple areas. And you have
He was
Gauss
an
and
alchemist
Euler.
as well.
Yeah, he was an alchemist also. A lot of people did not know, and he used to carry it secretly, and he used to suffer in silence because he was an honest man, and also he was a president of Royal Society, and he supported alchemy. So he tried to do that. He tried to figure out Vulcan and other things of sun, and he tried to replicate all sorts of things. So people had knowledge of all these things. But nowadays, what people have realized is this huge interconnectedness, and that brings us to the next topic of unreasonable effectiveness of mathematics. I don't see why it is so unreasonable. It may be unreasonable at Wigner's time, because that time at every point you have to understand that the very comparison between us and Newton was very different. Again, going back to Hariom, take that farmer that he spoke about, who comes and sits in the city. So assume that Newton comes today to Geneva and CERN, and he looks at the particle collider and our own models of quantum gravity and quantum field theory and so on and so forth. He may have gotten impressed with those things and carried away, but he would definitely see one thing for sure. He would still see the apples falling the same way. He would still see a lot of things the same way. So one has to definitely understand what is going on here. If the world has come about, and maybe he would have seen telecommunication and all of those things, but they don't exploit or contradict the laws of nature, so to speak. It's like saying that, people say, is homosexuality wrong? What do you mean by wrong? I mean, it does not contradict the laws of nature. I mean, laws of physics do not get violated because of that. So I think these sort of invariants that you carry around, that from the beginning of time till now, there has been this sort of very smooth continuity that speaks a lot about interconnectedness of fields. And just one more thing, I think, coming back to this example of a grand unified theory, and as Hariom is saying that you have to constantly update yourself. People always thought that, okay, we had a certain idea and we freeze it and that's over. If we fix like 8 problems, Newton had one problem, which is action at a distance, and later on it came to the point of Kelvin and other people. People thought that, okay, most of the problems in classical mechanics are fixed, and
done.
only
Yeah.
these few. So then came ultraviolet catastrophe and a lot of things, and that led to the foundations of quantum mechanics.
Quantum
I
physics.
think it is impossible at one point to answer all the questions, because the very answer that we are answering the question also assumes something called a nature of axioms and nature of laws and hypotheses. So it's as if you are standing inside a room and you cannot get out of the room, and you have to replace the room because you are getting richer and richer each day. You have to replace one tile with a better tile, one tile with a better tile. There's always one tile that you stand on that remains fixed. That is a simple mathematical theorem that you can prove using induction also. So there is always that one tile that you have to be standing on, and that you cannot move. I can just make up another example. You are in a room with a very good DSLR camera. How many pictures of the room you can capture? There's always one point that you cannot capture. Can anyone answer what is that one point that you cannot capture? You can take pictures of every single inch of the room, but one single picture you definitely cannot take. It's the picture of the camera itself. Or you can unless you have a mirror, then what happens is that you cannot take a picture of the camera at the back. Then you have another mirror. So the more you add things to that, the more this blind spot keeps moving. So we always have, just as biologically we have 2 blind spots in our retina, we tend to have these sort of blind spots, and that we pretty well know the reasons in psychology and philosophy, that as long as there's a divide between subject and object, there's always that questions that arise. And one of the interesting thing here to ask is that when Niels Bohr spoke about electron, is the same electron that we speak about these days? When Mendel spoke about gene, is it the same gene that we speak about these days? I think it's a very interesting question to ask, and I think there are a group of people who say yes and who say no also, because what the nature of problems that Mendel had, we have exact set of analogous issues with the gene concept right now. So science can never happen that one day all questions are answered and everything is sorted and we can just sit back and enjoy. That is only possible when with enlightenment, when you unlearn a lot of knowledge. But with science, it cannot happen, because the new knowledge that you introduce, you also introduce subtly in the form of an answer, multiple questions. So this trick, I think a physicist can do. And I think people like Hariom and other people who are excellent experimenters, I think they add up a lot of things, and they are somehow the judges actually. Because a lot of people go astray. You can commit a lot of things into pseudoscience and religion, and where is the end to it? For instance, even in mathematical space, there is a very famous theorem that it's infinite. You can have infinite theorems in mathematics and infinite facts, infinite axioms, so to speak, and they're irreducible, which is to say that you cannot have a group of theorems or group of facts in mathematics, or theory of everything in mathematics is also not possible, not just in physics. You may say, oh, physics, it's not possible because of real world. Even in your brain, even in mathematical, hypothetical, platonic world, theory of everything within mathematics is not possible. You cannot reduce all these axioms down into set of 10 axioms and say, oh, everything just is a result out of it. That is not possible at all. So I think this does address that there are a lot of questions, and right now there are even more questions. So if you take Hariom, he is working on a very specified field. So that field itself has new preprints coming up. If you go to ARXIV and other servers, just see every day 500, 600 papers are getting published. So even Hariom, who is extremely knowledgeable in that area, if he just goes out of the internet to some other place for a week or two, he would be, of course, outdated by a bit. He has to come back and read new researches in that. It's because of interconnectedness and the connectivity of the physics. In olden days, that got delayed because people had to write letters. I mean, Newton had to write a letter to Leibniz speaking about his calculus, but these days it's instant. And you can host it online and everybody can comment. So it's actually what Wikipedia's founder, Jimmy Wales, spoke about. It's the sum of all knowledge that is always greater than the sum of individual knowledge. So whole is always greater than sum of parts.
Thank you, Shyam. So I forgot to mention the name of the student who asked this question. It was Ruhi who had asked this question. There's one question that I think is directed towards Hariom. Neelam has asked this question. If we cannot see electrons, but we still assume that electrons and protons and quarks exist. So would you call these as a prediction, or will you consider it as a theory? And how do we differentiate between a prediction and a theory?
I think this is a very, very beautiful question. Given that we were in 1920s instead of 2020, just 100 years ago, this question is very aptly placed, because just then modern physics was emerging, and we were thinking about, okay, electrons, that one dot that we put which is going around the object. Perhaps depending on what class you're in, you've always studied a certain version of the atom. The simplest version of the atom is you just have blocks which are all stacked up. Then you have a slightly better version which says, okay, the proton at the nucleus is like the sun, and then like the earth, the electron goes around. Then we have a slightly advanced version, which is what happened near 1920s, which is, okay, no, electron is not like that. Electron is like a cloud. And so then what is really an electron? Okay, so it is very fascinating, right? Is electron a particle? Is electron a wave? The whole gamut of questions manifested as soon as we went into the realm of quantum physics. So then the question is electron real? Now, the job of a physicist, to be very honest with you, and particularly this is my perspective here as well, is to tell you what is happening in the world. And in order to tell you what is happening in the world, I have to say these things are there for the world to behave in this particular way. So that particular statement involves a theory. And the theory assumes certain elements, which are the bricks with which you construct the entire theory. Right? Now, what then happens is, of course, you made that as a brick into the entire construction. And you go and say, okay, if these bricks are laid this way, the wall should look like this. And therefore, you make a certain prediction. And based on that prediction, you test out a certain overall model. So what happened then? We assumed quantum theory is true. Then we did various certain experiments after that. And each of them increasingly and successfully established and reconfirmed that no matter how you put those bricks together, the wall that we predict is exactly the wall that we are seeing. Simple example, right? Transistor. Transistor was what? You put a certain bunch of materials in a particular manner, you pass electrical current through it, and then you have a certain gating effect. That gating effect was produced in a chunk this big. That was the original transistor, and now it is entirely powering your phones, right? So the fact that we have used our knowledge of electrons to behave in a certain way has allowed us to go from a chunk to the most modern technology. And therefore, we know that whether electron is true or not, the job of the physicist was to describe what is happening in the world. And that prediction of the world is correct, because then we have constructed an array of things which has worked. Now then comes the question of the absolute truth. Oh, is the electron actually there? And that is a very difficult question for a physicist to answer. It's a very good question for a philosopher to answer, and he may say yes or no, I don't know. But the job of a physicist is to tell you how the electron works, right? Rather than saying, is the electron there or not, okay? But of course, with every realm of understanding and development in science, we have development in technology. So right now, in the later half of the 20th century, and particularly in the recent times, we have something called the scanning tunneling electron microscope or transmission electron microscope. So we are going into the regime where you can place atoms and then you can look at the ripples of the electrons. So you don't have to imagine how the electrons will behave if you actually have a particular surface of a material and you actually place 20 atoms of copper on it, and the electrons are actually mobile. Then we know exactly, we can almost say that we can visualize the density of electrons. So we are at a technological growth and level where we can say, yes, we can see electrons. Just like how first they thought, okay, what is the construction of hereditary as we go from one to the other? They thought, oh, it's blood, which is why we still say, this is in his bloodline, this is in bloodline. Today we know blood has nothing to do with it. It's actually DNA, right? So in the same way, when we came into 1950s, Watson and Crick found, oh, this is the structure of DNA. This is how the DNA works. This is how cells produce it. Today we have technology to look at to the DNA. Is now DNA in controversy? Absolutely not, right? So prediction of yesterday becomes, with the help of today's technology, established fact. But then in doing so, you've pushed the knowledge boundary somewhere further. So which is why I said, if you look at 1920s, this question would have been imaginary. But to me today, functionally, electrons are there. There is no doubt about it, right? Firstly, their predictions work, but even with new technology available to us, we can still see, we can visualize them, we can image them, we can understand how they behave, right? And in that, I'm satisfied. Now, what is the fundamental nature of the electron? Is it one particle? Is it a wave? These questions are immaterial. And I think as a student of science, we should realize that there are certain questions, okay, no questions are stupid, but certain questions are irrelevant. And there are certain questions which are relevant. And the more you ask more relevant questions, the more you can contribute to the growth of science. Mm-hmm. Yeah. So I wouldn't say any question is stupid, but it's irrelevant. So you need to, like every student of science needs to develop an understanding of what is the boundary between relevant and irrelevant questions. And that will help you to become propagator of science rather than just a passive viewer of science. Okay. And likewise, you ask the bigger question when Sridhar asked the question. So you talk about electrons, you talk about quarks. So today, quark is just a theory. If somebody tells you that, okay, if you want to really split apart quarks and see the quark, you create more quarks in the middle, because the energy required to pull quarks apart is enough to create. So it's like a tautological argument, right? So maybe tomorrow we'll have a technology where we can see these objects, but right now we don't. Okay. but it's fine. I'm very happy to put that aside, somewhere in my imagination, and use that tool to create something beautiful. Now, when something happens where, and I will give this example. Okay, so somebody on the side actually asked me the question. J.J. Thomson proved it by cathode ray tube experiment that electrons exist, right? So it's actually correct. Okay, but the working model at that time was electrons behave like particles. And that is what the truth at that time was. Now, the problem is if you get stuck with that version of the truth, then when Bohr comes and says, no, electron is actually not a particle, it's a wave, suddenly now your world gets shaken, which is not helpful, because you have put your camera in the wrong spot. The tile has to be changed, as Shyam has very beautifully given that analogy, right? So you have put your frame of reference in the wrong place. So then what happened? Bohr said, no, the electron is not a particle. It has to behave like a wave as well. And then they realized, no, it depends like a particle depending on experiment that you do. It behaves like a wave depending on the experiment that you do. Okay, and this is very phenomenal, completely bizarre, completely illogical almost to the older classical theorists, but this is indeed what happened. And therefore, what we realize is that sometimes we have to give ourselves enough flexibility of imagination to not anchor on certain perspectives, and that will help us to build it. And when some experimental evidence comes which counters that, then you can easily, swiftly move about that fulcrum to go to another point of reference, and then you come up with a more holistic perspective. So this is the way I would like to answer the question, by saying that you have to think about what is the depth of that question, and does that really need that kind of validity at the moment to answer? Or are you willing to say, okay, I'm fine, I don't know everything, but this is good enough for now, let's move on, something like that.
So I think a related question to this point on prediction versus assumption, prediction versus theory, is Sanaya is asking, if we assume certain things and build a theory or build predictions around it, is it possible to prove those assumptions based on what it is built?
Based on the same theory or a different theory?
Different theory or whatever. Can you prove the assumptions?
Shyam, would you like to go?
Oh yeah, so I think this also relates to the earlier question about electrons, that what Hariom said, of course, it's 100% right, that you always need to separate that your scope of thing. Otherwise, you need to have certain sort of limitations to see. Otherwise, seeing itself becomes meaningless. If you have an image that has every single information within it, then that image itself, you cannot see anything out of it. So you need to always have a scope. But it's a very interesting question, and also I will tell you why is it that these set of questions, that why is it that philosophy somehow is coming back into science right now, and why is there a whole field of philosophy of science that even scientists are approaching and learning something from? Because Niels Bohr famously declared that after quantum mechanics, physics is again philosophy. Because I think I would start by asking that, okay, so there are two different things here. So if you take a theory and you have axioms of that theory, you have maybe in physics, assume that for the heck of it, I mean, this is not how science is done. Assume that electron is an axiom. You're not supposed to question it. What you can question is what can be constructed out of it. In the same way, if you have a textbook, you don't question why A is written like that. Can you ask that? I mean, I never got any question from any student coming to me and saying that, why is A written like that? They don't ask. But they would always ask that, why is electron real? And why is electron the way it is? So it's not just that electrons are relevant to our smartphones that they are asking this question. I think the way the science and the pedagogy of science, the way it is presented, this sort of point is not infused through. I mean, you never find any English teacher getting this question that why are alphabets written the way they are? Because people clearly know that they are just conventional in a sense. And what you get out of these alphabets are beautiful language and then understanding. So you never question those alphabets because they are just having a role of a placeholder. So one of the very interesting thing that why is it that philosophy can shape up the physics and experiment is that things like CERN and Large Hadron Collider, there is always a case in the history that where experiment has added up to the theory and where theory has added up to the experiment. It's a symbiotic process. You cannot for sure say that always it is the experiment that led to theories, or always that it's the theories that led to experiments later on to confirm them. It's a symbiotic thing. It's a sort of an Escher's drawing hand. You have one thing drawing each other. So what happens is that now CERN is, I mean, of course, Marcus gave a wonderful presentation. CERN is now trying to build a very bigger particle accelerator, and there's a huge amount of funding that is going into that. So people have to just understand and also put these limitations, that how is it that these conventions, because English language, you don't ask questions like A, but in physics, you definitely, the whole hinge lies in these electrons and subatomic particles. So you have to, at the end of the day, know, and many philosophers, including Quine and Putnam, who are very good physicists also, because they studied with Hans Rickenbach, who was a contemporary of Einstein. They knew quantum mechanics quite well. They asked, it's perfectly valid. You can come up with a theory that all the universe is made up of unicorns. Okay, perfectly valid. It's given. Universe is made up of very minute unicorns, or universe is made up of Donald Trumps, very microscopic Donald Trumps. Okay, so this definitely is permissible within science. But why do you call that a trash theory? Is that Donald Trump, you cannot attribute certain causal things that you can attribute to an electron. So then you have to very carefully understand, are we speaking about the name? So do you have a problem with this word electron? Or you're asking what this electron refers to, that thing. So you have to clearly separate between the map and the territory, so I call it. So what happens is that here, Murray Gell-Mann, who was a very famous physicist and a Nobel Prize winning scientist, there is a very famous thing called realism. And realism is the notion that what do you consider as real? I mean, you don't consider the iPad as real, iPad in its own form, because iPad is not accountable by the laws of physics. What is real inside the iPad are the electrons, protons, and neutrons. iPad is just a human construct. For you, it's an iPad. I can use it as a paperweight in a parallel universe where I don't know what to do with an iPad. So what happens here is that Murray Gell-Mann thought that the quarks, because he was a person who named quarks. So he is a sort of a father, or he performed the naming ceremony of the quarks. So he thought quarks are just placeholders. So if you think quarks are just placeholders, so tomorrow it's not important if it's quark or if it's some other thing, some other composition, that proved to be very fatal, because the minute you think something as a placeholder, a quark being a placeholder, like an X, you replace electron with an X, and you say, okay, this is X. There is a different mathematics that approach that you take. And if you think that quark is definitely a quark, it is not some other bark. It's not a tree bark. So if you cannot replace a quark with a tree bark, you take a different set of mathematics. And if you take quark as a tree bark, you have a different set of mathematics. So here, a physicist and a mathematician and a philosopher have to converge. They have to agree whether electron is real or not. So I think this somehow I would try to give a hint of why is it that sometimes, as Hariom perfectly said, because Hariom, I think people like him should be speaking, because I think as there was a very famous painting of Socrates. Socrates was least respected in his time, apart from his students. There's a very famous portrait by Raphael, I guess, where Socrates is sitting on the in front of the house, and his wife Xanthippe pours a whole jug of water onto him, because he's useless. Basically, he's a philosopher who speaks about what is the nature of universe and all of that, but he cannot earn for the family. So I think Hariom is very right, because he's an experimental physicist, and he is the one who is proving and who is actually inviting the funds to physics. Why would people fund? Why, if you have to go and ask people like Donald Trump, who do not believe in climate change, which is right on your face, climate change, how can you go? And so I think Hariom has definitive authority to say that, you have to limit your scope like this. But what happens is that if you go at the level of foundations, and this is a beautiful thing of science again, science is constructed in such a way that you can safely ignore everything at the bottom of it, which is to say that to use an iPhone, you don't need to know how an iPhone functions. And that is a wonderful thing, isn't it? I mean, we just take it for granted. You don't have to know how an iPhone works or a transistor works. You can just use it. And that is a privilege that this culture has given. So what happens is that in olden days, things like selfies and electronic chips, even right now, an illiterate will go to a shop and say that andar chip kharab ho gaya. He does not know what is a chip, but he somehow knows it so well. He knows that chip is causally connected to the phone. So one of the privilege of science is that it can, of course, you can do biology without knowing chemistry. You can do chemistry without knowing quantum mechanics fully. You can do quantum mechanics without knowing a lot of other things. It's good if you know a lot of things, but they are sealed off from each other. That's why in agriculture, you never see Higgs boson. You just see a mass of crops being produced, but you never ask that, oh, there is no mention of Higgs boson because recently it was invented. So I think the sealing of fields is very important for this sort of a thing. But sometimes, very surprisingly, that these are the philosophical questions, whether an electron is a real thing or an entity, like a chair or a table, does make a lot of difference, because we have stitched this electron into a lot of mathematical framework, and depending upon whether it's a wave or a particle or a field or anything else, the mathematics that is used is different. So I have spoken to a lot of physicists who are very, very famous, starting from Roger Penrose and a lot of people. The best answer I got, what is an electron, is what they thought was it's a solution to a Dirac's equation. They don't even know if it's real or not. It's always a solution to Dirac's equation, and that's all.
Exactly.
And again, that I think it brings us back to the question of unreasonable effectiveness of mathematics. That why is it that you just completely ignore real world and you hinge all the burden on mathematics? And that is a deciding point for you. Because why is it that electron cannot exist, neither does iPad, but it's only a solution to Dirac's equation? Would you be comfortable knowing that your life is a collection of a lot of solutions of Dirac's equation? I mean, I'm not Shyam and he's not Hariom, and a passport officer comes and walks in and asks, who are you? And I say, oh, I'm a lot of solutions to Dirac's equation. I mean, I just feel very mechanically reduced to something that is dead. And this is another thing that we have to deal down when you do these sort of reductions. That you have to also understand that science gives a very limited picture, and you have to, of course, combine it with a lot of narratives from cognitive science, from culture, from all of these things, and then make a holistic narrative out of it. But as Hariom said, there's always a scope. Yeah.
No, I think this is a very interesting point that you have mentioned here, and this automatically brings us to the statement of emergence. So I would like to explain to students who are a little bit younger, right? So Shyam mentioned about the statement of unreasonable effectiveness of mathematics. So just to relate to some examples that you guys can think of in your very basic level sciences, you would have studied, for example, Newton's laws. Okay, very simple, very basic idea. Or you might have even heard of vectors. Okay, I'm assuming that students here know vector. Sridhar, is that a fair assumption?
Yes.
Okay. So when you're talking about a vector, for example, and you study, okay, now there is a box here, and if this box is pushed, this box can move in this X direction, in Y direction, or in Z direction, and depending on the kind of the push, it works, right? And so then what do we say? Okay, this is actually a vector that can be described. So the motion of an object can be described by the language of vector. Okay, and then for those of you who know mathematics of vectors very well, then you know, oh, okay, if I add one vector to another vector, I get another vector within the same vector space. And there is a certain rules that bind vectors that now suddenly describe how boxes would behave if they interact with each other. So when Shyam says unreasonable effectiveness of mathematics in describing the universe, it goes to show that we were talking about boxes interacting with each other, but hey, if we describe one box as a behavior of a vector, we realize, oh, okay, all these vectors, the way they interact with each other, can actually be applied to all boxes. And then you can imagine, okay, very beautiful, everywhere this applies. Now then you say, oh, what about energy? Oh, no, energy is actually not a vector. Energy is a scalar. And the way scalars behave in mathematics, for those of you who know, they follow number theory. They don't follow vectors. And therefore, the way in which these objects will behave is very different from the way in which vectors will behave. And then if you're slightly more exposed to advanced quantum mechanics, you realize, oh, actually, even energy is not only a scalar, it is actually a tensor, or it is actually a matrix, or a position and momentum are matrix. And then when you involve that language of matrices into understanding of position and momentum, suddenly you realize, okay, I cannot think of position and now as a mere vector. It is actually a vector of matrices, which is already very complex to think of. I don't want to go into the mathematics of these things, but when we start describing them that way, we realize everything falls into place. The entire structure of physics can be described very beautifully. And therefore, the statement, I think probably Feynman coined this. I don't remember who coined this. I think probably Feynman. Is it Shyam?
Oh, what statement?
The unreasonable effectiveness of mathematics?
No, Wigner.
Wigner,
Eugene
okay.
Wigner.
Okay.
Eugene Wigner.
Right. So he's also a very famous physicist, right? And quantum person who contributed to quantum physics as well. So this is why we say that mathematics is so unreasonably beautiful and effective in describing the modern world. Now, then I want to come back to the second point that Shyam made. So we talk about various levels, and very beautifully Shyam said that if you're doing biology, it's okay if you don't understand chemistry. If you're a biochemist, okay, you need to understand chemistry, but you don't need to understand, deeper levels of quantum chemistry. If you're a chemist, you don't need to understand physics. If you're a physicist, you don't need to understand. If you're a molecular physicist, you don't need to understand quark physics. Okay, and if you're a quark physicist, you don't need to understand string theory or supersymmetry or whatever. Okay, whatever is the modern approach here, I don't know. So you are sealed off. But this is a very interesting point, and I want to slightly mention a particular perspective. Now, have you gone, or have you seen some of those videos where you go and you watch the birds, that are going in a big swarm? Okay, now what happens there? These birds, if one bird, they follow very large patterns, and they all tend to be moving in a certain way. Ants tend to do that, birds tend to do that, fish in the ocean tend to do that, right? So is there some laws of physics that they're communicating with each other and they're doing that? Okay. Is there some deeper picture there? Okay. The reason why I'm trying to say this is that there are times when individual object behaves like very well-defined rules, but when those individual objects come together, they behave in a certain manner, but then there is also some new phenomenon which comes all together in a very different perspective, and that is called emergence. So, a very simple way to think about it is that if you put 1 and 1 together, you only get 2. Okay, but if you have one vector of magnitude 1 and one vector of magnitude 1, it is not a vector of magnitude 2. You get something else, right? So this is a very simple difference of how vector calculus works. But more fundamentally, there is an emergence of something new from basic fundamental things, and that emergent thing cannot be described as a sum of its parts. And this is called emergence. Okay. Now, emergence happens in various systems that are often nonlinear, and there is a whole dimension of physics called chaos physics or nonlinear physics. And one simple example is, for example, water. Okay, you go and see water. Water is what made of water molecules, okay, which are separated by a certain distance between each other. But then you can have turbulent flow of water. You can have vortex in a water. You can have various features in water, which has got nothing to do with the molecular description of water. And these new layers of manifestations happen not just because of the fact that there are two different layers, but also because of the fact that there is a nonlinear behavior of that system, right? So it's very interesting. And as the system becomes combination of more and more and more objects, you'll realize that this complexity or this interconnectedness, pardon me, Shyam, if I'm mingling words here, but this nonlinearity starts to manifest, which then leads to emergence. Okay, and fortunately, in physics, many of the equations are quite linear. Whether you look at Schrödinger equation or Dirac equation, these are all linear equations, and therefore our life is very straightforward. So we can just shut our brains, and the continuity manifests. But then there are times when nonlinear physics manifests, and then you get a little surprised, because then the reduction of approaches cannot work anymore. Something new has to happen altogether. So all this was discovered very recently in the last 50, 60 years, and this is not modern physics. This is called classical physics, but it's called chaos theory or nonlinear physics. And we have essentially been able to appreciate all these things because we have had much better computers. Thanks to Turing and people of the like, we have had computers, so we can do things that we cannot imagine by physically doing these calculations. And we can imagine what these nonlinear equations look like. And they bring a new picture to this entire game. And this game that I was talking about, which Shyam has mentioned, it's called reductionism. So if you say, I start from this object, okay, then there is always something underneath. There is always something underneath, and I can keep on building it like that. So a reductionist would say, okay, if I start from the body cells, then I can predict, okay, the body cells are controlled by proteins. What is proteins? Proteins are made up of molecules. What is molecule? Molecule is made of atom. Atom made of quarks. Electrons and protons. Electron, proton, okay, some of them are made of subatomic. You keep on going down, down, down. and there is a systematic way up, and you start putting things up, and then you can reconstruct the entire universe. But an emergence guy would say, hey, wait a minute, no, that is not really agreeable to me, because independent of the constituents, when I go to a certain level of complexity, something new happens altogether. And this is something very fascinating, where our reductionist approaches don't work, and we should be appreciating the fact that the nature is not that easy to understand. She's always having some trick up her sleeve, right? So this dichotomy of reductionism versus unable to employ reductionism is something that we need to keep in mind as scientists. And not just say, okay, everything I'll just shove it under the rug and move on.
Okay, so we also have viewers on YouTube, and there is a question that has come up from a YouTube viewer, and I'm going to expand on that question. So the question is, do you think that God particle can be discovered? But I'm going to put it in a larger context. So David Hilbert, a famous mathematician, had once mentioned that 100 years later, if he comes out of his grave, he would ask whether Raymond's hypothesis is proved or not. So so he believed that there are certain ideas that are not provable, at least to his understanding. And last year we had a mathematical physicist, Andre Leclerc from University of Cambridge, who came up with some ideas which he thought that can be used to prove Raymond's hypothesis. So he's a physicist, but he came up with some ideas in math. Similarly, we know of pure mathematicians who have also made some contributions to ideas in physics. So it's not just that people from physics to some extent are applied mathematicians, but there are also pure mathematicians who occasionally contribute to this field. So one question is, how do you see this collaboration, and has this compartmentalization in the last many years hurt the discoveries? Because in 18th century or 19th century, I think there was more connection between these two fields than what you see today, because we have all the departments and how the incentive structure is created, etc., etc. And the second question related to the God particle thing is, are there theories that you believe that in our lifetimes, for example, will be difficult to verify or difficult to prove, if I may use that word, through experimental ways?
Hariom, you want to go ahead, or should I go?
Maybe Shyam, you can answer first. You can answer first.
Okay.
Go ahead.
So I think there's a lot of information packed into that. Of course, I would see why Hilbert thought that he wanted to know whether Riemann hypothesis was fixed, because it was so tempting to see that it is right, and it did not prove out to be the way it is. But regarding the God particle, okay, firstly I have to first clarify, it was never a God particle, it was a goddamn particle, because they wanted to find out that goddamn particle.
Yes,
and later on it was, I think you should ask Marcus and other physicists, and physicists will be really angry if you go and tell them that, oh, what is a God particle? There is no God particle. People thought that the Higgs field, I mean, to just give an introduction, what happened was that things like electromagnetism and gravitation are long range forces. So let me just give a very brief tour into that. So if you are carrying a torch or a or a candle inside on a dark alley, okay, so when the candle is really, when you're going far away, you see the brightness is like dimming down to a point of zero, right, for a human eye. But if there's a physicist called David Deutsch who has done this experiment, a thought experiment, of course, and that's one of the luxuries. It's a completely different thing. You should look up what are thought experiments and how are they different from actual experiments, and why do they even predict the things that actual experiments cannot predict. So that's a different topic altogether. So David Deutsch, who is the founder of quantum computing, he speaks in his book about frogs. So when frogs can see individual photons, though we can see individual photons also, we have a different notion because we have a XY axis on our eyes at the back of a two-dimensional set of rods and cones that fire, and then that projects onto the third dimension. So though we detect, we need some more information. We cannot individually distinguish between two photons. But whereas what a frog sees when this lantern goes away and away and away is that it actually sees it flickering, which is to say that this frog is actually able to see one particle after the other, one particle after the other, one particle after the other. So it could see that. So one of the questions that people like Steven Weinberg and Glasgow and Abdul Salam and other people had that time was to distinguish between these things. Why is it that gravity can spread out all through the universe and electromagnetism also? They're long range forces. And why is it that these things, there are two forces. One is a strong force and one is a weak force inside that. They are not long at all. I mean, how do you explain that? So it's a beautiful thing that I think it's a sort of a puzzle that you push one piece here and you wait. So you get an antique piece, a lock from a era of Egypt of where they used to do mummification. And then you don't know how to open the lock. So what you do at the end of the day is that you turn a lock and you take the risk, maybe a poisonous gas will come out and you may die. So that is a risk that you take here, which is the same risk of working on a theory for 20 years and proving it wrong, which is a sort of or even committing suicide that Boltzmann has done because atoms were not accepted at that time. But what happens is that you turn the lock and you realize, okay, one piece is moving here, the other piece has to move here. What can be fixed in that sense? So what people thought that was that the strong and weak forces had two different answers altogether. Strong force is confined, which is to say it is in such a way that there is a sort of a it is confined in a region of space, which is a sort of a ball that it somehow absorbs and it collides within itself. So it can never go out. And we know that it's responsible because of quarks that are there inside it that do not let it go away. But whereas a weak force, and you have to also understand that everything that is long range definitely has to travel at the speed of light. It has to be massless. So these are of course, it's a very hard thing to explain how the mass should be zero and so on and so forth. But it's a postulate that arises that if it has to be long range, by intuition also that it has to have less mass. It should just zip away through the space at the speed of light. So that is an assumption. But whereas in the weak force, we know that the W and Z bosons actually have some mass. And that is a sort of a contradiction to the math. So at that point, so I think the intelligence of a physicist is to decide between should he be hell-bent on a theory or on experiment or on math. So I think a best scientist is somebody who is so dynamic and who is a sort of a cat who can quickly jump. And this is what Aristotle called the sign of an intelligent mind, to entertain an idea without accepting it. So what a physicist can do is that he can quickly figure out with his intellect that, okay, this is not agreeing with math. So I can drop math and invent a whole new math. That can be done. Or this experiment can be interpreted in a different way. Or my physical whole ontology of the universe can be made in a different way. So there are these three choices that everyone has to make. And these three choices are not easy because you cannot say, oh, it's my whim, I can choose mathematics. You have to let the whole community agree. So again, here the community comes. The sociology of science is very important. This community has to agree because it's as if the physics is sort of a thing like this. You go onto an island where people speak a very weird language. You have no clue about it, what this language is. And they refer, every time a donkey goes, they call it klipka. And you don't know what that word means. Are they referring to donkey, donkey's teeth, donkey's eye, donkey's tail? You don't know, but they are just pointing to that thing. But we don't know what that means. So after a long time, humans have no trouble understanding these words. I mean, when you are taught what is a chair, you are never told that chair always has 4 legs, or it has handrest, or it's brown in color. You are given an image. And isn't it contradictory that our basic thing, the way we are taught the chair, if you're intelligent, you will point out that, but this is not the chair that I was taught about. And I see a lot of chairs. I mean, a chair with only 3 legs is also a chair. You still call it, oh chair, that's a broken chair removed. That's still a chair. So you don't have a fixed definition, but you can accept a whole infinite objects into the ontology. That is by learning. And that is where somehow the mathematics also comes into the play, which is to say that there are some things that our senses cannot see. There are some areas that our hands cannot touch. Definitely at the quantum level, though our hands are constructed out of quantum level, we cannot go and touch an individual electron and see and poke it and say, oh, are you moving this side or that side? So you need a very interesting apparatus. And there are two apparatus like that. One is a telescope, which I love, and microscope. These are two scopes, but the scope of them are so different. You have somehow invented that apart from your eyes, you can actually jump out of your own senses and see something that your eyes can never permit you to see. So mathematics is another sense here that will help you see the reality as it is. And it's a very interesting thing. Suppose, I don't know if you have ever seen this result. I'll just write down here 1 plus 2 plus 3 plus 4 plus and so on. Have you seen this infinite series? 1 plus 2 plus 3 plus 4 and so on. So of course, by our intuition, it should diverge. It should lead to infinity. But the whole of modern physics, especially string theory, and if you study a little bit of quantum field theory, you need to know this technique called renormalization, where these sort of series sum up and they have to converge on a finite value. Which is to say that 1 plus 2 plus 3 plus 4 and so on leads to minus 1 by 2. There's a very simple trick. I think you can ask Hari or Vinay. They'll be easily able to explain how this series can converge into minus 1 by 2. And there are it's called Ramanujan summation, and people can explain it easily. But the issue is that when you have something like this, why after a long time I thought that how is it that a meaningless set of marks, because if I go and give it to a tribal and I say, oh, this is very important equation, please keep it safely because this is grand unified theory, give it to the world, he'll just throw it away because it's meaningless for him. How is it that a meaningless pieces of marks that we write with an ink on a paper relate to the way the galaxies move, relate to the way the semiconductors move and work and so on? So this sort of causal link, how is it that this pen and paper can connect to the galaxy out there? So that is one level of answering. And we definitely know that it's not the pen and the paper, because you can write mathematics on a board, on a LaTeX document in a typesetting. So it has nothing to do with pen and paper or ink for that matter. So then we go into a little more deeper definition of mathematics, which has only logic and set theory. So most of the mathematics, safely I can say, of course, I don't know, there are mathematicians on the board, but I can safely assume that mathematics is only a combination of set theory and logic so far. I mean, at least the mathematics that physicists use. So why is it that unreasonable? I recently, after a long series of reflections, I figured out that there is nothing unreasonable about it. It's like saying that you have learned, say, Hindi and English, and you call a chair as kurchi I don't know what you call in Hindi. What do you call a chair in Hindi? I don't know Hindi well.
Kursi.
Kursi, right? Okay, so kursi. So kursi and chair. So now it's like asking that how is it that the Hindi word kursi explains the English word so beautifully? Does it explain? No. So one of the answers that I have thought about and I can conjecture is that there is no unreasonable effectiveness. Of course, Wigner thought there was unreasonable effectiveness because he saw pi coming up at weird places. Pi has to do with circumference of diameter to circumference of diameter, right? It's a ratio between circumference and diameter. And he thought, how can pi sit in black holes and thermodynamics and everywhere? So are there circles there, small circles everywhere around? So when people speak about black holes, of course, we know it can be circular in a picture. And again, I'll come back to the picture of a black hole later. But we don't know that there are circles in the deep down. So what is happening here is that he could not understand. But right now, we can at least understand that there is no unreasonable effectiveness of mathematics, which is to say that mathematics and physics are connected to the human ways of thinking, which is generalized thinking. And these are two different modes of thinking. We use one mode because you don't know that if you go to a village where nobody uses Hindi, you have to, nobody uses English, you have to use Hindi. And that way you cannot figure out that why is this Hindi so unreasonably effective here. You have chosen a domain where a mathematics which is related to the set theory and the laws of logic. Set theory are just numbers, 1, 2, 3, 4, and so on and so forth. And they are also related to logic back again. Logic again goes back to the human reasoning itself. So when you are trying to explain a physical phenomena using mathematics, it's not the mathematical power that is there in it, but it's somehow the way we have created mathematics and the way we have carved it. We have done it in such a beautiful way that it always carries within it a subtle between the lines, if you read between the lines of equations, it always has this human intellect and intuition between. And that is what we try to ignore when we go into physics, which is to say that is why it looks unreasonably effective. But when you see physics and mathematics are two different, very good fields addressing these two things, you definitely know that, okay, there is no unreasonable effectiveness here. They are just two ways of thinking about the thing. And one way is what we are employing to do that. And that comes back to the title of can you physics and maths? Of course, that's what we have been doing so far. And that is a nature that unreasonable effectiveness then becomes that how is it that our thoughts connect to the universe? And that is a question in interest, maybe interest to some philosophers, but physicists, if you look at, as again I said, if you look at how is it that this hand lifts some rice and puts into my mouth, if you just look at hand and head and you don't know that there is a brain inside that sends a message to the ligament and that lifts in and there is a conscious intention, you just look at it as paradox. Is there a magnetic force between my hand and my mouth that attracts the rice onto my mouth? Only when their plate is there. And if otherwise, my hand just goes away from the mouth. Assume that somebody just puts a poison and just tries to like pull it here. Then it acts as repulsive. So it's exactly the whole scientific enterprise is like this, because we are inside the system. We are just looking at hand and mouth as different. But science gradually is stepping out. And how do you step out is one of the things is to marry, not physically marry, but marry between the fields. When you marry two fields, you get a complex field, which is to say biology and chemistry, biology and mathematics. Mathematics also 34 fields are there. And then you marry between these things, algebraic number theory, arithmetic geometry, arithmetic topology, algebraic geometry, and so on and so forth. When you keep marrying, you step out of the universe. You step out of that universe and you go into a broader thing. Then you will see, oh, it's because the human has an intent, this hand goes away. It's not because of some magnetic loss. In the same way, an alien should not look at the Indian roads and think that all cars have some magnets that repel each other. It's not because of that. We don't want to dash into the other car. That is an actual explanation. But if you're an alien observing the earth and making the predictions, this repulsive model perfectly works. Can you deny that? No, you cannot deny that. You think that all cars can be modeled as a magnets and they're traveling on the road. There's always a distance that they don't dash into. And when they dash into, I can say that, oh, the magnet is becoming weaker and weaker and it has lost its magnetism. That's a perfectly valid theory from alien watching from somewhere else. But the another theory is that we don't want to dash into the car because car has some economic unit and we don't want to lose that economic theory. And how do I get that? Is because I stepped out of this picture and I've seen the global implications of why these things don't fit into each other. So there's always this thing that you have to step out and see it as holistic thing. Science is always holistic, but whereas experimental physics, what Hariom is trying to do, tomorrow he's a wonderful experimenter. So he cannot sit down and think, oh, what is my implication of this to a universe or the existential questions that are there. He has to just work on what is there in front of him. So it's up to you as a physicist tomorrow, whether you want to answer the big questions. What is the purpose of life? What is the nature of universe? What is the nature of God particle, so to speak, in your terms, or anything of that sort, or you have to just get busy and do the things around me. I don't care about all of that. I'll just care about what can I do that is more concrete. So that is depending upon our taste, and I think both paths are okay.
Thank you, Shyam.
So I think I just want to make a statement here. I think Shyam has very beautifully narrated a perspective, and very very smoothly he has tried to say that mathematics is not unreasonably effective in prediction of science. But here, I would just like all of us to just think about one thing, and I'm not trying to answer or debate Shyam's point, but to think about something here. Shyam mentioned that when the universe is working, okay, we go and have our mathematical theories. And what is mathematical theories? He said two things, and I know very little about math. I must say that at the beginning itself. He said that there is set theory and there is logic, and then with that you can construct mathematics, at least good parts of it. Of course, there is a certain reduction in the statement, but which he acknowledges. But nonetheless, the fact that logic is what is required to construct mathematics is undeniable. Now the question that we need to ask ourselves is, the reason why mathematics is working very effectively to describe nature is because it is based on logical structures. But why does nature have to follow logic? the fact that nature is following logic allows us to use mathematics to describe that. And in that question lies the wonderment that is the reason why we're able to use mathematics to describe nature. But we just got lucky. You just landed up in the street, and you happen to be in Mumbai, and you go in Chembur, and suddenly you start talking Tamil, and you just happen to be lucky that people around you can understand Tamil, right? So in the same way, we just happen to get lucky that nature actually uses logic. But why? Nature does not have to use logic. And therefore, I think I still hold to my view that that we have gotten extremely lucky on landing up in mathematics as a tool to describe physics or sciences in general, and therefore it is very effective, and it's phenomenally beautifully effective, even wonderfully so beyond my logical reason to answer. Because why logic is working, that is beyond logic. I don't know how to answer that question.
Yeah, because that's a blind spot that we stand upon, and I think you are right. That's the point that I wanted to come into, but I just forgot because this is not a real classroom, and I am missing a lot of points. I think Einstein has beautifully summarized the most incomprehensible thing about the universe is not because it exists, that's okay, but the very fact that it is comprehensible, that is incomprehensible. So why is it that nature has to follow certain laws, and why are these laws so simple and beautiful? Why is it that like that? Is nature greedy? And that's a very different argument altogether. So that's a beautiful line of thought. Yeah.
I hate to do this. I am torn between being a moderator for this session and being an audience for this session. I would love to be an audience, and I don't want this to end, but unfortunately I have to wear the hat of a moderator, and we only have a couple of minutes left. So quickly, can you tell us what are the challenges that a researcher faces so that it will be relevant for the students who are thinking about going ahead in the field of research? And then we will come to concluding remarks. So it's going to be very short. I'm so sorry to do this. I'm so sorry for the students to do this because there are so many questions. I'm completely overwhelmed by the questions, but unfortunately I couldn't take all the questions. So I apologize to the students, and we would make sure that you have a conversation. So quickly, over to you. Sorry.
I think Hariom is best and answer.
Yeah, let me address this. Let me address this question. So I think research, when you start off as a student, is a very fantastical thing. I started off when I was probably very much in your age, in my 8th to 9th classes, and then I got very dreamy-eyed, and I thought, I want to understand very fascinating stuff about Newton's laws, and I stumbled into quantum physics, and I stumbled into relativity, and I was asking questions like, okay, how is time, and can we do time travel, and things like that. So I had a very fantastical perspective, which was very much driven by fantastic ideas and images that you read in your books, and I think that's a very beautiful, important first step for you to enter into the subject. But at the same time, being a student of science is different from being a researcher in science, and the difference lies in that as a student you're a passive appreciator. Okay, you can really appreciate. You can have all the intelligence to appreciate, and that's completely fine. But when you put on the lab coat, okay, your mind lab coat, it does not have to be physically a lab. Okay, you go and do Gedanken experiments or thought experiments like Einstein did, or you do your physical experiments. It's both are equally fantastic. The question then becomes that you will be faced with stuff in front of you which does not align with what you had thought about the process. You will discover results that you had not conceived of, or even worse still, if you're an experimentalist, the tools that are required to make that experiment happen, those tools are not working. Like, it's not a very simple thing like saying that, okay, I want to write my equation down, but my pen is not working. This is a very trivial example, but something like that, And but this is different because you can continue. If you don't have a pen, you use a sketch pen. But now these kind of tools and equipments are so important, are so fascinating. If they stop working, suddenly the entire experiment goes haywire. Like, simple example, right? The sun, you have a very large ring, and you have so many pumps which are attached to the system. If one pump fails and the ring starts to leak, that's it. The entire experiment goes off. And is there some intelligent thinking process here? No, it is just the mundane, boring stuff of life. Some oil was leaking from somewhere, some nut was not screwed properly. This does not require high-level intelligence, but this is the day in and day life of a researcher. So being a researcher means that you are able to face failure you're able to embrace failure, and you're able to use failure to even push yourself into new dimensions of thinking. And often, this is exactly what has happened. The failure of the ability to apply Newtonian physics led Einstein to think of, okay, there is something, there is no spooky action at a distance. You really, I'm using the spooky action about quantum entanglement, but I don't mean about that. But there's no long range effects. You really need to have time for effects to propagate from one place to the other. And then the failure of one particular work becomes the stepping stone for somebody else. So I think all of you are some of the most smartest, brightest students in your circles, in your communities, in your classrooms. You're some of the topmost guys, and that is verily so, because you have the very beautiful intelligence and intellect. But at the same time, that same intellect, you should have the ability to use that and to deal with failure, to deal with the boring, the mundane things, and to realize that you have to appreciate that. Now, one simple example that really touched all of our hearts was Chandrayaan. Okay, I think all of you know about Chandrayaan and how it failed, right? We didn't manage to land. But as a physicist, the fact that, to me, I was extremely moved by that, because as we went, we launched ourselves, we created an orbiter, and that orbiter landed somewhere because of some technical failure. Technical failure means what? Maybe something was turbulent in that nearby proximity, or maybe the jet engine, malfunctioned, something, and it is really mundane, and that has crippled everything. But in that failure, you get to appreciate the raw nature in her nakedness, and that is beautiful. And we need to appreciate nature, no matter how harsh she is. And in that, I think, lies the joy of a scientist, the joy of the failure in science as well, as much as success. I think success is very beautiful, but even failure is very beautiful. And I think this vision is really important to be a researcher rather than just a mere appreciator. I think I was certainly not circumspect. I'm sorry.
Shyam, do you want to add something to that, or you want to
conclude? No,
I think concluding remarks?
He has. Yeah, I think what Hariom said is wonderfully fine. I mean, you ask Marcus, why are you doing the things that you do? I think the most important advice that I can give people, which I did not give myself, because that time we are not well equipped. I mean, the way you are all, because you have wonderful mentors around you, is that I think you should only do things that you are really passionate about. So the question of whether doing science or anything of that sort, that is up to you. But are you really passionate about it? That is something that you have to really find out, because you are going to spend next 40 years of time working on something. You don't know its implication, whether it's going to be right or whether it's going to be wrong, unless if it's not going to be your only intellectual pursuit and only intellectual happiness, and regardless of the world, that's when you succeed as a physicist. Otherwise, if you go to physics to win a Nobel Prize or to become a millionaire by solving Millennium Prize problems, I think it's better to rob a bank. You will get $1 million very easily, because you will if you go to solve Riemann hypothesis to only get $1 million, that's not the way things work, because you will be really disappointed sometime, because you build up a lot of things and you always see according to your own viewpoint, and suddenly some people will come and say that, oh, all that you have done is wrong or can be looked at a different way. Then that hurts you. So that's why I'm always trying to emphasize that you should be dynamic and fluid. You should be able to take defeat at the face of it. If somebody comes up with the better conclusions and more reasonable arguments, you should just put aside your ego and say that, oh, that's good, that's great. And you should also be able to live for your ideas. So there's a healthy balance between that, being totally eccentric and self-absorbed and being totally fluid also. That's also meaningless, because if you're extremely fluid, you don't have any hope at all. So
anchor. You don't have anchor.
You don't have an anchor. So the best thing I could say is the discussion between Gandhi and Tagore, because Tagore was a very sort of a Sufi saint, sort of a person who was open to a lot of things, and he was open to the Western culture also. But whereas Gandhi was quite conservative. So what Gandhi said was that I am open to keep my windows open to the Western wind, but I don't want my feet to be blown away by it. So it's always better that you stand on certain field and you see how much you have to fight for it and how much you have to go with it. And I think this is only possible when you remove all the aspects of society, money, fame, and you actually address, are you really passionate about that idea that you're working on? why do you get up in the morning? Why do people like Marcus and Hariom get up and go to the lab? I mean, is it for fame? I don't think so, because I think he'll be better, more famous if he does other things. I mean, he will be, it's even more tougher to take this path. So what drives them is the innate passion to understand the purpose of universe and their own contribution to it. And that's alone. If they get fame, if they get some awards, if they get some appreciation, okay, that's good. But that is not what that drives them. So unless you have that in you, unless you don't sleep in the night because of some problem that you're actually like struggling to understand, it's better that you can choose a lot of other fields, because this is not going to be easy. I mean, right now a lot of funding is also coming into science, but it's not as lucrative as other fields. If you are a software engineer or some other thing, you can earn more. So you have to be able to be a little bit sacrificial about a lot of aspects, and that you do when you are extremely passionate about the ideas, and that you don't shiver around. Yeah.
Thank you so much, Hariom and Shyam, for those wonderful thoughts. We are running out of time, unfortunately, but we have requests from many students that they are totally hooked to this conversation and would like to have a part 2 of Can You Physics a Math conversation.
Sure.
And
I mean, if
with
you're not late here, I mean, if there's no other session that is starting, we are happy to take some other sessions. I don't some other questions right now. I don't know if Hariom is busy right now.
I may have to leave. I may have to leave
okay.
because I'm occupied with some other appointments. But I think definitely let's. I'm very happy to have a part 2. Let me just throw this question at the moment. I mean, I don't want to throw your plans into the wrench into your plans, Hari and Vinay. But Shyam, are you available tomorrow?
Yes.
Because I was supposed to have a lecture. Instead of me having a lecture, I'm very happy to continue on with this conversation. It'll help me to, address and answer these questions of the students. And if Shyam is available, let's just figure out what time that is. Let's, instead of me giving a research topic theme discussion, I think this conversation, is very beautiful, and we should continue with that.
Great, that will be great. And students are also voting for that. They would love to have a part 2, and they are fine with we doing it tomorrow if you both are available. Thank you so much for doing that at this 11th hour and agreeing to continue with this conversation. Yes. So with that, let us conclude today's session. And I would like to thank all our viewers on YouTube and Facebook who have joined us live and taking out time. We appreciate you taking out time and joining us. Thank you so much for doing that. And we also have a faculty from University of Ljubljana, Slovenia. His name is Professor Damian Kobal, and he has specially joined for this conversation. Wow. And he took a session for the kids on conic section, and it was a fabulous session because I don't think we get to learn conics in the way he taught. And we have seen from the comments that students have made how beautiful that session was. So let me ask Ashwat Jain, who is from batch D, to give a vote of thanks for today's session. Ashwat, over to you.
It has been a true pleasure, sir, attending this session. This wonderful dialogue between Shyam sir and Hariom sir, it's between theoretical and an experimental physicist. It has truly brought all of us to a sense of deep realization. I have been privileged enough to have contact with Shyam sir in the previous editions of RAMTP. A couple of years ago, he took a session on fractals, and I'm extremely happy to have conducted a session on the same this year in RAMTP itself. So this session, it's a beautiful manifestation, a sneak peek you could call it, into the true depth of physics. We would like to thank you, Hariom sir and Shyam sir, for this absolutely amazing session and for taking out your time for all of us and raising the scientist and raising a mathematician. Thank you so much, sir.
Thank you, Ashwat. And thank you, audience. Thank you, students. And thank you, Hariom and Shyam, for this wonderful conversation. See you tomorrow. I'm pretty excited to moderate the session tomorrow as well.
Sure.
And see you all. Bye-bye.
Okay. Take care. Bye.
Bye.
The streaming is stopping.